So let's get started. Okay. So hopefully I'll keep everyone awake today, both here and at home. So I know. So we are going to talk more about confidence intervals today. This is an important concept in statistics, but they can be a little bit tricky. So we will. There's a lot of things it's easy to be confused about, and that's natural. And we saw a lot of those things on the lecture on Tuesday, and we're going to start with kind of a review, and there's more. I think mostly you've seen the most important concepts here. But we'll see kind of more examples of how to use them and kind of and more refined uses of them. And we'll go over more kind of some conceptual things we haven't quite gone over with as much yet. For the class, okay, so where are we on the schedule? Let me mention a couple of things. Homework 5 was just due yesterday. We're still in the late period of that, so hopefully the hiccups on our end didn't kind of delay stuff too much. Hopefully that will all be, the last few will be still turned in. We did finish grading homework 4 again, so that they haven't been posted over to Canvas yet, but it's basically done. So I think by the end of the day that should be posted. And now homework 6 is out. Okay, so homework 6 is officially posted. This is homework 6 is the second to last homework. Okay, so if you get this one done the end of today, then you only have one homework left. Okay, so maybe go and do it, and then you're almost done. That would be cool. Okay, so this is going to be on estimators and confidence intervals. I think the first couple of questions are going to be pretty straightforward. I just want you to kind of get practice reinforcing, calculate the sample mean, the sample variance, make sure to look up exactly what I mean by the sample variance to get full points. And the median, these are all things that should be straightforward. Then apply the central limit theorem in general. Was the expected value of an average, the variance, and then use central limit theorem, kind of the normal approximation to approximate this. This is with the uniform distribution. So it's a very just simple example of this. Again, should be pretty straightforward application. Question 3 will probably be the tricky one, where you're looking to create an estimator for something a little bit, for a parameter we haven't really looked at creating an estimator before. So you have to think a little bit on this question. And we try to break it down into pieces, so it's not too bad. But you'll have to think a little bit on question 3. Question 4 is kind of using R, right? So it should be a pretty straightforward extension of the of what we've done in R, and some things we'll actually do in the lecture, probably not today, but probably on Tuesday. The very last question here. Okay, so that's homework 6. Okay, so again, I'll tell you not to wait to the last minute, but probably most of you will do it a little before the deadline. But you could basically do almost all of it now, which is why it's coming out now, even though it's not due for like a week and a half. Okay, great. And again, there'll be a quiz today. Some people, let's remind them there are quizzes every week, Thursday or Friday. Yes, okay. Confidence intervals. Okay, let's just start with the like a review of these sample. We're going to start with the sample x1 through x2 up to xn. These are random variables. These are random variables drawn IID, so they're independent and identically from some distribution that has a parameter. Let me use, what was I use F for the generic distribution? Let's say, yeah, for some distribution, F of, so theta, okay, parameterized by theta, okay, and if we want to create an, so an and so like an estimator would be a statistic, which is going to be some function of x1 up through xn. Okay, so again, theta hat is going to be a random variable, and it would be biased if we looked at theta hat, it's a random variable. So if we looked at its expected value, and that was exactly the true parameter value. Remember, this guy is a constant, right? It is defined precisely here. It is what the parameter used to generate that distribution. It's a fixed quantity, whereas this guy is a random variable, right? So it has a distribution. And one way of looking at kind of how well are we kind of understanding the true parameter theta is say, here's a process that in expectation gives the right value, right? And then what we've been talking about starting on Tuesday was a confidence interval. Okay, and in particular, we wanted to look at a 100 1 minus alpha. So like percent confidence interval. An example would be e.g. alpha equals 0.5, 0.05. That would be a 95 percent confidence interval. Okay, and what would this look like? This would be, we want to look at theta, this true parameter theta, and somehow give some statistics based on the random sample we draw that says something now about a probabilistic notion of this, not just the expected value, but some notion of the probability that this parameter is so contained in some bounds. Okay, and so we're going to use ln and rn, and we say the probability is less than is equal to 1 minus alpha. Okay, so this alpha, is the probability we have failure in our bounds, that we're outside the bounds. So a 0.5% would mean 1 out of 20 of our attempts to do this did not work. Okay, and again, we have random variables. Now our random variables are this ln and rn. The probability in the statement is over the choice of the ln and rn. These are guesses, right? So these are random variables. Okay. And so the probabilistic statement is over these, not over theta. Theta is the constant, what we want to know, but we don't really know where this actually is. Okay. And in particular, we looked at if we have an example for ln was when we did xn bar, right, which is the average of the sample, minus z alpha over 2 sigma over square root n. This is if we kind of we assumed it looked, these were normal, so random variables, or we kind of approximate xn bar. If it made sense to approximate that with a normal distribution, then the z alpha n was this parameter we could use to kind of tell us how much to scale it, and also depended on the variance or standard deviation of the random variables. That's the sigma, and also the n, the number of samples. The interval should be smaller if we have more samples or averaging, right? And so similarly, Rn was equal to xn bar plus this. So same value. All right, so this is pretty much what we talked about on Tuesday. How if it looked like a normal random variable, which by the central limit theorem, if you average a bunch of stuff together, it looks like a normal random variable. Then these are pretty good ways of getting a confidence interval, assuming that you think xn bar looks like a normal random. Yeah. An estimator is going to be a random variable that's a statistic of your sample. Okay, so yeah, so this is a kind of when you're used to thinking about statistics like so colloquially, you're looking at actual observations, right? You're looking at actual recorded values. And what we want to do is we want to reason about what those recorded values might be if they were drawn from a distribution before we actually look at them. We want to design an algorithm or an analysis before we look at the data, because we don't want the data to, and so for instance, does taking the average of all the data points make sense? And how much sense does that make? Well, we can analyze it by thinking, well, what if we drew n observations? And that's what those random variables are. And say, if we drew them, well, in expectation, it gives us a good estimator of the mean. Now we can go look at the data and say, I'm going to look at the data and take the sample average of it and say, I know if these were drawn randomly, then they would give me a good estimate of the mean. I don't know if they're drawn randomly, but if I assume that they were, then that would be a good estimate of the mean, and that it gives in expectation is the right thing. Okay, but it could have some variance to it, right? And how much variance, how far off do I think it's going to be? That's confidence intervals helps us answer that. Yeah. Yeah, so one standard deviation away gives you, if you look at a normal distribution and you walk out one standard deviation, what fraction of the probability is within one standard deviation? It's about 64%, right? Well, I want 90, let's say I want 95%, right? So I need to walk out more than that, right? How much more? Well, it turns out for 95%, for Z 0.025, which would be 0.05 divided by 2, then this equals about 1.96. So I need to go at one standard deviation, about 2 standard deviations. Then about 95% of the mass of the probability lies within 2 standard deviations. If I want to get 99%, then I need to go out almost 3 standard deviations. Right, and so this value, the Z alpha over 2, well, that value tells me how many standard deviations out do I need to go to get that much of the probability. The standard deviation, yeah, so what this transformation is doing, remember, we started by saying that we understand that there's this other random variable, Zn, which is xn bar minus mu square root n. This this is exactly from a normal random variable with mean 0 and standard deviation 1. Okay, if I take xn bar and I subtract off the true mean, which I may or may not know, and divide by the true standard deviation of xn bar, right? This is the standard deviation. This is standard deviation of xn bar, and sigma equals standard deviation of x, right? So to get the standard deviation of xn bar, I need to divide by square root n. The variance goes down at a rate of 1 over n. The standard deviation is the square root of variance, so it goes down at the rate of 1 over square root, right? And so I can analyze this, and this we kind of build pre-computed some tables, right? So I know, like, there's a table for alpha and z alpha over 2. Oh, spam call. Thought I had silenced. Okay. For alpha over 2, and I know that 0.05 z alpha over 2 is 1.96, 0.01, then this is 2.58. It's like 0.005. This is approximately 3. Okay, so there's a table I can look up based on this normal distribution, right? And I can say, okay, for this choice of alpha, this is how much I want to scale this. The scale term comes up in here. That tells me how far to shift this out. And I can go from that expression. So I don't have Zn. I don't have that random variable. I have xn bar, right? This is the one I actually have. But I can algebraically, I can multiply by the standard deviation on both sides, and I can subtract the mean from both sides, right? The true mean I'd like to estimate, right? And that true mean is like this, is the theta parameter. Or I want to actually subtract xn bar and multiply by -1, right? But I can solve for, so I can say Zn equals x bar minus mu over sigma square root n. Now I can say that means sigma square root n Zn is equal to x bar minus mu. And that means that mu is equal to x bar minus sigma square root n times, so Zn, right? So I can rewrite, I'm basically solving for the random variable, for the parameter mu, but both of these quantities are random variables. And so I only actually have xn bar. I don't have Zn. But I say, well, how big would it need to be for it to be that this difference is going to be unlikely? And that I can look up in a table. So this is what we reviewed talked about on Tuesday. And that gives us these normal bounds for the confidence interval. Okay, look, I want to give another, before we're going to talk about like Bernoulli random variables, and you will see kind of an application of this. And then, but before I do that, I want to say, kind of give a different view of what's happening with the confidence intervals, is that I'm going to kind of be getting these two. So there's some underlying random process, and I'm going to get ln and so Rn. And these are random variables here, okay? And then I want to, but so if I were to do this on actual data, there's actually a distribution on these. It's a joint distribution on these. So I'm going to try but ignore the fact that it's a joint distribution on these things. So these are actually random variables. They're not actual points on here. What I can think of is I actually get some sort of, so I don't actually, again, these are, so random, so variables. So you know, so not kind of scalar, so quantities, right? So these are not scalar quantities. But instead, what I can think about is, let's say I get an interval here that's ln, and so Rn. Okay, when I drop to lowercase letters, these means these represent actual observations. So I'm gonna run my algorithm, my algorithm for constructing the lower and the upper bounds of the confidence interval from some actually observed data, and I'm gonna get actual values on this. Okay, these may not be the actual quantity that contains, you know, I want the true parameter I'm trying to estimate to fall in between these values, right? So I want that there's some true value. Let's say that it's theta. I want theta to actually fall in here. And I hope that, if I drew 95% so confidence intervals, and I estimated them this way, then for each instance I observe, there's a 95% chance that theta actually so falls in here. So if I repeat, now I'm going to say, let's repeat 20 times. Okay, so I'm going to repeat this 20 times for, so let's say, for kind of 95% so confidence intervals. Okay, so what should I expect? I'm going to get another, say this was 1, this is ln 2, this might be ln, this would be, so Rn2, right? And to kind of keep track of, these are joint things, so I'm going to start drawing them as like these so circles. This would be number 3, right? Where this is the bound. Maybe sometimes it's over here. This is 4. Sometimes it's over here. So it's larger. Maybe it's centered, right? And I'm going to get a whole bunch of these so circles. Okay, so it's looking, so, you know, it's kind of a mess here. So let's, okay, so let's say I have 20 of these, okay? And there's one interesting one, this one here. I didn't draw it quite right. This one here does not contain the true value of so theta. This one I circled did not contain so theta. So I would kind of expect that if I drew 20 of these through this random process, one of the confidence intervals I drew did not contain the true value here. That's what the confidence intervals are saying. I can, if I generate bounds from this random process 20 times, if it's a 95% so confidence interval, then basically I would expect probabilistically one of them, 1 out of the 20 would not contain it, and 19 out of the 20 probably would contain the true value. Okay, so the confidence intervals are a procedure that gives me a set of bounds which I hope are correct, and are correct about 95% of the time. Right, but it's not a guarantee that the true value is actually in there. And the actual confidence intervals is this random process. Right, so every time I collect new data, I expect to get a different confidence interval here. Right, so kind of the procedure I'm analyzing, right? I'm going to get random, I'm analyzing the process I'm going to do, where I'm going to get the random samples, I'm going to construct it. How well do I expect this process to work? But when I actually do it, I only get one, right? If I do my process, I'm only going to get one confidence interval, but I'm only 95% confident that the true parameter is in those bounds. It might be right in expectation if I have an unbiased estimator. If my unbiased estimator is in between those, then in expectation, I'm going to get some. They're going to be on either side, but maybe 1 out of 20 times I'm wrong. Okay. All right. Okay. So this is kind of this process of kind of drawing these circles or these intervals. Those random intervals, usually 95% of the time, or 1 minus alpha times 100% of the time, contain the right parameter. Is there a question? Nope. So, okay, so the ones on the top, those don't actually exist as actual values. Each of those, there's actually, think of this, there's actually kind of like a probability distribution of where this is, right? Those aren't actual locations, those are random variables, so they have a probability distribution, right? The bottom ones are the realizations. And the realizations works because, but not always, right? They don't always work. And so, in fact, I've chosen, if I wanted them to always work, or say work 99.99% of the time, well, then I would construct them to be much wider. And I could much more confidently say, well, the true parameter is in there, but I'm not really giving a very small range of what the true parameter is, so it's not really as useful. So I want to balance this, how useful is it, how narrow is the interval, with how confident am I in the interval. There are kind of two things at play here, the width of it and the confidence in it. Yeah. Yeah. No, usually I'm more confident in that my parameter is in that interval, right? If I make the confidence intervals wider, I'm more likely to catch it, right? So if I say, kind of I'm saying, where is the population center of, so Utah, among people, say, who voted for, so Mike Lee in the last election. Okay, so I don't actually know who's going to vote for someone, let's say the next election, right? So who's going to vote for, so Spencer Cox when he's up for re-election? Where's the probability mass of that, right? In Utah. So I could say, well, I know the probability mass of the density of Utah, but I don't know who's going to vote for who, right? So where people are going to vote for is going to shift that probability mass. Now I say, I don't know where it's going to be. I can maybe get an expectation. That would be like an estimator. Or I could say, well, I think it's going to be in this region. And if I make that region so big that it contains all of state of Utah, then I'm going to be pretty confident it's correct. But if I make it really small, I'm not going to be that confident that is actually the right value, because I've been too specific. I'm very specific, but I'm not very confident. Or I can be very confident, but not very specific. As n gets bigger, I can be confident and specific. Yeah. Yes, that's correct. Right, good. Right, so that big ln, big Rn are random variables, and each, on the bottom, each of the small ln Rns, or a circle which kind of captures both, is a realization drawn from the distribution of the random variables, big ln, so like big Rn, right? And I've chosen those, so 95% of the time, the true parameter will fall in that range. That means 5% of the time, it won't fall in that range, right? So you're not completely confident. You're only 95% so confident. So good. Okay, great. Let's go through, let's go through a concrete example here. Yeah, so let's look at the, so I'm going to take the, so I want to, so I want to do something like, so like understand the kind of the mean, so snowpack, right, above, say, so like 7,000 feet in like the Wasatch. Okay, so I want to estimate the snowpack. This is, you know, kind of, so interesting this year, we have a very high, so snowpack. It's in many locations, we've already seen more than we've ever measured in the past, but not all locations yet. And so how you would do this and how they actually try and measure this is they will use, they will sample n so locations. Okay, so let's say n is equal to, so 40. So they put 40 different stations out in the mountains, and at those 40 different stations, they're measuring how much, so like how deep the snow is, right? And so we're gonna say we kind of know that the variance among kind of the observations, sigma squared, we're going to say this is 36 inches. Okay, I don't know if this is accurate or not. Let's say it's 36 inches. Okay, so we're assuming we know the variance. Next week, Tuesday, we'll see what to do if we don't know the variance. Okay, but for now, we know the variance. And we're going to say that we're going to now, so compute that x n bar, right? So these, I'm going to sample these locations, x1 up to xn. Xn bar, let's say, is 620 inches. Yeah. Yes. Yeah, good. Right. So these are, yeah, if we're actually computing it, we should call this a lowercase xn bar. Okay. Okay, so we're actually going to compute the confidence interval on some actual data now. Okay. And so let's compute now the 95% so confidence interval. So okay, so of the so average so snowpack, right? So let's say this is mu. Okay, so how would I compute this? So like, how would I try to compute this so confidence interval? Okay. Yeah, okay, great. So I'm going to use a z alpha over 2, and this I'll use z alpha. I'm going to have, this means alpha equals 0.05. So I want 0.025. 0.025, and I know this is 1.96. Okay, there's a table, you can look this up. Yeah, and back. Yeah, so you can calculate an R. We saw do this on Tuesday. This is a common one. If you do this enough, you'll just remember it. But there's a table, you can look it up. Yeah. So okay. So now I want to create this actual interval where I think, you know, based on my assuming these are normal kind of random variables distributed with variance 36 inches, that I'm going to have 95% chance of containing the true value in there. All right, so how would I do this? I have my z alpha over 2. What else do I need? I have my xn bar, I have my variance, and I have n. Okay, so what was the formula we had for the lower confidence interval? What was, I'm going to get ln, this lower bound. Anyone remember what this was? Yeah. Yeah. Times probably sigma over root n. Okay, yeah, right. So this is the right bound. We can plug in what we have here. This is 620 minus 1.96 times, so square root of 36, that's 6, divided by square root of 40. Square root of 40 is square root of 40. Okay, that's slightly more than 6. Okay, and so this is going to be so 6 over square root of 40 is going to be let's say slightly more than 1, so we're going to get approximately 600 about 618 inches. Okay, and was the upper bound going to be Rn? It's going to be similar here, right? It's going to be xn bar plus z 0.025 times sigma over square root n. Okay, and so that equals, again, 620 plus 1.96 times 6 over square root of 40, and this is approximately 622 inches. Okay, so this is the interval, is going to be from 618 inches, 622. So inches. So, okay, does this seem realistic? Does this seem about right? My width of my interval, I say 95% of the time, based on my estimate, the width of the interval is only going to be 4 inches. Right? So if I measure my average at these 40 locations is going to be 620, I'm off by, be plus or minus 2 inches from the true average. So Snowpack. Yeah. Yeah, so you're saying you think this variance looks, this interval looks pretty small, right? Like I've got, I'm questioning that too. That looks so pretty small to me. And you're saying the issue with this in our modeling or in the process was maybe n was too small, like I divided. Yeah, right. There's some elevations like at the ski resorts, they get much more snow than, some other locations, right? And the north facing slopes have more snow than the south facing because of the sun. And there's a lot of other things that play into the variance here. Yeah, the variance is saying the standard deviation is 6 inches just by looking at one of the locations. If I just pick one location, the true value within I can get roughly 95% by going out 2 standard deviations. That's 12 inches, right? When I'm sitting at 620, that seems like that's probably unrealistic. So probably I would guess that this part, this is probably too small, to be true. The rest of the numbers, xn bar 620, that's in the right. So ballpark. There are actually, they do measure it with about 40 stations. So it's not, that's about right. But that variance is probably is probably too low. But this is how you do the calculations. Okay, so if the variance was like if I thought the standard deviation should be like 60 inches, right? Then what would the variance be? Like 60 inches seems like maybe that's about the right variance. So this at 60 inches be about the right standard deviation. So then the variance would be it might be 3,600. This should be inches squared, right? Right. So the variance 3,600 inches squared, right? So that seems about closer to what the right thing would be. And then how would that factor through this 6? That would cause this 6 to be a 60 here, right? This would be a 60, and then I would get that'd be about a factor 10 bigger. And now I would say that's about between 610 and 630 inches. Okay, this seems reasonable, right? I have now say, well, the average snowpack is probably between 610, 630. If I really thought I had 40 uniform samples, right, from this, and I average them all together, I can get a pretty good estimate. The central limit theorem says as I get more and more data, my estimate gets better and better. So if these are really IID estimates of the snowpack, then this should actually be about right. They're probably not IID samples, right? They're probably placed more in locations where they can't place them, but they try to spread them out to get a good estimate of this. Okay, great. So this is kind of an example of how we would go and do it. And it's always good after you do it to go look at the numbers. Say, did these numbers actually make sense, right? Did my assumptions going into here actually seem reasonable? Yeah. Yeah, these work for estimating the mean. Yeah, I'm trying to estimate a parameter by taking, I'm averaging the mean. That's a pretty common thing to do, usually, but yeah, these are for estimating the mean or the average of something. Yeah. Yeah, it's just standing for whatever this table, okay? And actually, this table is, say I've got, again, Zn, or let's just say Z, if Z is from a normal 1, right, then that means that this is equal to E, well, there's 1 over square root of 2 pi e to the negative x squared divided by 2. This is the standard normal distribution for like a value x. Okay, and now I want to say, right? So this is this is the normal. This is for a PDF of x if the PDF describes a normal, so like random variable. Okay, and so there's some distribution 0 and about standard deviation of 1. Okay, and now I want to come up with a value. This would be z alpha over 2, so that if I integrated under the tail here, that this integral, the integral from z alpha over 2 to infinity of so x f of x dx is going to be equal to alpha over 2, right? So if I integrated the area under that curve, right? No, I don't need this x here. I just integrated the area under the curve, and that's what that expression is saying, that is equal to alpha over 2, right? Remember, the whole integral is 1 because I use that weird coefficient in front. And so I want to pick the value z alpha, so if I integrate in this way, right? Now, this does not have a closed form expression. This is one of those weird things that comes up a lot, that there isn't actually, I couldn't simplify and tell you that integral is actually this formula, otherwise I would, but it's this thing that is stored in tables inside of computers that is looked up. It's called like the ERF function or these other things. It's built into R, so R can do it for you. Yes. Are you given a z? Well, we are given x and bar, and we argued that I can convert from x and bar. I can convert from x and bar to z. I can always convert from x and bar to z if I know mu, sigma, and n using this formula. So I can actually then solve for mu, and that gives me this formula for the lower and upper bounds. We went through this also on Tuesday. Okay, so we aren't given z, but we're given x and bar, and we say we can always convert it and algebra and this and so it looks like z and bar, and then if we did that z alpha, that lowercase z alpha over 2 is the correct scaling parameter to convert it. Yeah. Correct. Yeah, alpha is given to you in this class. It's given to you as if you go out and do statistics in the wild, you have to say, what is a confidence I want to, try and report? I want to say I have 95% confidence. You choose that as a modeler, depending on how much confidence versus how much specificity you want. Yeah, but alpha is given to you, and so then it tells you you can look this up in a table. And how you calculate it was solving that integral. And then algebraic, I mean, you'd probably kind of, they actually kind of did like a binary search until they got the right value, right? Because you can't actually solve it algebraically or calculus. Yeah. Yeah, I'd say like the width of the confidence interval would be the right way to think about that. Yeah, so if the width of the confidence interval is small, then that's more specific. And if, yeah. Okay, okay, this is good. These are all good questions. I think hopefully this is honing in your understanding of this. I'm going to talk about a use case of this called the margin of error in poles. Okay, so if you, this is in the spring, typically if you teach this class in the fall, it's during when there's some sort of US elections happening, and you see lots of reports of polls about how do we think someone's going to vote in the next election. Okay, and these confidence intervals show up in how they report the results of the polls, okay, in a way called margin of error. And so we're going to kind of go through and explain that. And the margin of error will basically be a 95% confidence interval, okay, or it's going to be the half the width of a 95% confidence interval. It's basically what the margin of error for polls are going to be. And so I'm going to try and derive that, okay? So typically you ask n, so let's say random, so let's say likely, so voters, okay, and they're going to say, let's say one, if let's use, so like Spencer Cox for an example, if vote for Cox, and 0 if vote if so not. Okay, so we're gonna kind of, this could be a question. Usually they're more complicated, but this is the kind of the core of it. If there are multiple people running, and or if they haven't made up their mind, then proper polling should try and do that sort of stuff. But we're just going to look at this case. Okay, so if you ask a random person, and every time you ask an independent random person, what does this look like? A random variable we've talked about? The result of one question here in front. Bernoulli, yes, great. So this is basically a Bernoulli, so random variable, right? So this will be xi from a Bernoulli random variable, and is parameterized, usually BER, parameterized with one value p, and p is the probability of like having a 1, right? So we think if 60% of people are going to vote for, of likely voters are actually going to vote for Cox, well then p would be 0.6 in this, right? That'd be 0.6, you get a 1, and 0.4 that you get a 0. Okay, so this is Bernoulli random variable, but they're going to ask n random voters, right? So what they're probably going to do is say, so report how many, so let's just say, so voters said, so yes for, so Cox, right? So if I add these up, let's call this S equals xi equals 1 up to n of, or the sum of xi up to 1. Okay, so this is also, it's a combination of random variables. S is also a random variable. Okay, what do we know about random variable S? Yep. It's what? It's not the mean. The mean would be I take the average. I specifically am not taking the average here. I will in a second, but yeah. It's not an exponent. Is that what you? X bar. I don't want to get X bar yet. No, X bar would be if I divided by 1 over n here. But I'm not doing that. Yeah. It's not an expectation. This is a different name. I'm looking for another name of a random variable. S takes a special form that we've talked about in class. So theta? No, theta would be kind of like an example parameter. It's a discrete random variable, right? It's a number, an integer, it's a count. So there's a name of this, okay? Let me called binomial. So this is a binomial random variable, and S would be a binomial random variable. Binomial takes in 2 parameters. One of them is p, and the other parameter is n. Okay, this was another random variable that we looked at. I think it was homework 4, you had to look at binomial random variables and do a plot, right? What do we know about binomial random variables? We know that the expectation of S is going to be exactly n times p, and the variance of S is going to be, what is this? N times P times 1 minus P. So we know this about the binomial random variable. Okay, if I ask N people and a question, what fraction of them had, and each of them said yes with probability P, how many do I expect to say yes? This is a binomial random variable. And we also have looked at that this looks a lot like a normal random variable. If I do S divided by N, and now this is equal to X bar, okay? So this one is equal to Xn bar, but, okay? This is going to approximately, I'll do approximately, come from a normal distribution, okay, with now the expected value divided by N, so with value P, and variance is going to be P1 minus P divided by N. Right? If I push through a 1 over N into an expectation, it factors out 1 over N. So I get back NP divided by N, I get just back P. With the variance, if I have a 1 over N in the variance, it gets passed out as a 1 over N squared. So I have from a times N times P 1 minus P to a divided by N squared. So now I get a divided by N. All right, so it looks like a normal random variable. And I think on your homework, you actually should have plotted this, where you plot the binomial distribution as the bars, and you plotted the normal distribution as the curve, and they kind of look like each other, okay? So we're gonna say, because the average of these Bernoulli random variables looks like a normal random variable, we're going to try and create a 95% so confidence interval for S over N, which is the fraction of people who will vote for Cox. Okay, so we're going to try and now say, S over N would be an estimator of the fraction of people of P. P is the quantity we want, but now we want to create a confidence interval for this. Okay, yeah. Okay, that's what we're going to see. Good. This is what you should be thinking. Yeah, how big do they make these polls and how accurate are they? Right? We're about to see that. Yeah. A binomial random variable is a sum of n Bernoulli random variables. That's what it is, by definition. It's confusing, probably. Good thing to review these things before the final. But yes, so that's exactly what a binomial random variable is. And then we kind of know this approximates, looks like a normal as n gets large enough. So now we're going to treat it like a normal distribution and create confidence intervals like we did before. Yeah. By the time you get to n equals 100, it's pretty close. Yeah, we're going to have to go. Our polls are going to have to be larger, more than 100 people already, to get good confidence intervals. Okay, so we're going to kind of we're going to need numbers larger than where this looks like a normal. Okay, so yeah, that's a good question to ask. Yeah, we don't exactly have a normal, so why are we using these things? This will just be easy application. This is typically how they calculate it. You can calculate the exact confidence interval for binomial random variables. But if you remember the binomial distribution, it would involve like the n choose k times p to some power and 1 minus p to some other power. And it was kind of a mess to work with, right? I'd rather work with the parameterized continuous distribution because it's much easier to work with. I have my Z alpha tables. I can look those up. Everything's kind of a lot easier. And so they're pretty close. By central limit theorem, I actually know it's going to start looking like this. For binomials, I know after about n equals 100, they're about as close as you can see with your eye. They're aside from the discreteness of it. But in terms of this, the areas under the tails, it looks quite close. Yeah, in fact, we'll see. You probably don't want to survey less than roughly 1,000 people. Even 100 people, you're not going to get very good at. So the confidence intervals. Okay, so now we wanted to look at this poll and say, what are the confidence intervals? How accurate is this? Okay, so the 95%, so confidence, so interval. Okay, and remember we have n p 1 minus p times p divided by n. Okay, and I want to know kind of, so that tells me now I have, nice thing is I have the variance here, right? So I have the variance. So that's given to me in this situation. So I want to now apply this ln. It's going to be xn bar, which was my Sn over n. This is my sample estimator minus z alpha over 2 times the standard deviation, which is going to be p 1 minus p divided by n. Okay. Okay, so let's see. I'm going to use a trick to say p 1 minus p is going to be less than or equal to 0.25 for p in 0, 1. Okay, this is maximized. The variance is largest when p equals 1/2. So I'm just going to say, okay, p1 minus p, I'm going to upper bound this by 0.25. This is typically, it's not that interesting. If 90% of people are going to vote for Cox, then the variance might be a bit lower, but it doesn't matter. He's going to win. So the interesting case is when it's close to 0.5. So I'll just use that bound. So I'll put a 0.25 in there. So I'm going to say this is xn bar minus 1.96 times 0.25 over n, the square root of this. Okay, and then okay, so this is the lower bound, and the margin of error is typically reported as this. This would be the margin of error, is what this quantity is. And so, yeah, so if I surveyed 100 people, what is the margin of error going to be, right? So percentage, right? This percentage is going to be the margin of error. Let's try this. 1.96 times the square root of 0.25 is 0.5. Divide by a square root of 100, let's say for n equals 100, then this would be square root of 100. So this would be 1.96 times 0.5 divided by 10. Did I do this right? Yeah, so this is equal to, times, hold on, 5 by 10. Hold on. This is 100. So this number times 100, that percent. Okay, so this would be about 0.098, and then I would say times 100 percent, so approximately 9.8 percent. Okay, so if I estimated 60% of people are going to vote for Cox, right? I'm saying, well, my margin of error is between 50 and 70%. Just is not that helpful, right? If I'm below 50%, then he's not going to win, right? But that's a pretty big lead. Like 60% is a pretty big lead in politics. It's usually pretty safe. So this is not very helpful. So if I wanted to get to say, what's and I'm going to skip this for time, but let's say I wanted a margin of error of, say, 3%, right? So that seems maybe reasonable. If you look at a lot of polls, they're roughly at 3% margin of error. This is not uncommon. How many people do I need to survey? If I do some algebra here, I will need n equals to 1,067. Okay? So if I get about 3% margin of error, that means if the right answer was, if I estimate 60, I'd say that's between 57 and 63. That seems a reasonable estimate, right? If he has a comfortable lead, you're pretty confident in that. 95% of the time, that's what it'll actually be if you have 1,000 people in a poll. So a lot of polls will shoot for this number, right? They'll shoot for about 1,000, or often they'll try and hit 1,067 because that gives you 3% some margin of error. Okay, and so this is a common size of an individual poll, but then you can aggregate polls and do better. Yeah. So I'm saying I didn't do the calculation in blue. It's actually it's in the notes if you look in the notes, but I want to switch to kind of a quick review for the quiz. But if I were to say I wanted to solve for 9.8%, but instead set that equal to 3% and then solve for what I need for n, right? Then this is how big n would need to be. Oh, yeah, let me write this more clearly. This is 0.5. Yeah, this is the square root of 0.25. So that's a 0.5. So is that what you're asking? Sorry. Yep. Yeah, it's also, oh man, that does look a lot like a 3. Okay. That should be a 5. Great. Oh, that was a bad handwriting error. Okay. Okay, great. So to analyze, understand how accurate these polls are. Now, polls have a whole bunch of other challenges with them, and that's really hard to get a random sample of people. And so they do a lot of other stuff. And if you ask me again on next lecture, I'm happy to go into that a bit. But they can't actually get a full random sample of people, but they try and replicate this and deal with this in some other ways. But if they could, and it was probably when like 95% of people had like landlines and were home in the evening, which maybe was the case like 20, 30 years ago, then this would be a pretty good way of doing this. They would call people on your phone, on the phone in the home in the evening, and they would get a pretty good kind of random sample of people in some areas. So, okay, great. So remember this next politics season if you want to look at the polls. All right, so okay, let's do a quick review of what the important things to understand on the quiz. Okay. Yeah, so this quiz is about confidence, so intervals. Okay, and so these are a pair of statistics. Okay, so these are random variables, ln and rn, from a sample x1 through xn from some unknown distribution with some, but we know that we're assuming a family of distributions, but there's some unknown, so known, so parameter. Okay. Okay, and so, and what they say is that you kind of remember that you get ln less than this parameter greater is less than Rn is equal to 1 minus alpha. If this is a 1 minus alpha 100%, so confidence, so interval. Okay, so if you do you understand what this means? You should be able to do pretty well on so the quiz. Okay, if there's some part of this which is a little bit confusing, then kind of then you should ask about it, right? This is ideas that we've been building up over the course of the semester. All right, so the additional new ideas are all here, but there's a lot of parts of this that have been kind of developing over the semester. Kind of the other thing to keep in mind is that ln, so if we're to, so a confidence, so interval for the, so mean, which is so common, is ln is equal to xn bar minus z alpha over 2 times sigma over square root n. And Rn is similar here. Z alpha over 2 times sigma square root n. All right, so some things to kind of think about this is like what happens if we, so things that might be useful to think about, if we increase, so alpha, or if we increase n, or if we increase, so sigma. So what's going to happen to this sort of confidence there? All right, so think of what happens if you increase alpha. Alpha is the probability that you can be wrong. So if we increase alpha, that means we're allowing more probability of being wrong. That means Z alpha is going to get smaller. And so our interval is going to get tighter. We're going to have less confidence, but more specificity. A smaller interval, but less confidence if we increase alpha. Okay? If we increase n, what happens? Okay, we're getting a better and better estimate of the mean, right? Central limit theorem says we get a better and better estimate. Means that the central limit theorem tells us the variance is smaller, but we can also look at this and say what happens to the confidence interval. If n gets bigger, right, then this n shows up here. I'm dividing by a larger number. And so the part I'm expanding around my sample mean is getting smaller because I'm dividing. If we went from polling 100 people to 1,000 people, we went from like from 10 percentage points to about 3 percentage points. So we got a smaller interval around our estimate if n increases. Okay, so n increases, we get a smaller interval, right? So this would be the, let's say, the interval size. For alpha, if we increase alpha, the interval size is going to go down. If we increase n, the interval size is going to go down. If we increase sigma, the standard deviation, the thing we're estimating with each observation having more variation, right? Sigma is in the numerator here, right? It's in here. And so if sigma gets larger, then the interval gets larger. So now this increases. So if we increase alpha, we get a smaller interval. If we increase n, we get a smaller interval. If we increase sigma, the standard deviation, we're going to get a larger interval. All right, so kind of being able to understand and ask questions about these things, or answer questions about these things are things I expect you to be able to do after these couple of lectures. Yeah. Yeah, alpha is usually given to you, right? So usually you say, if I don't give you alpha, it probably means like 95% confidence interval, alpha equals 0.05, right? So it doesn't necessarily increase alpha. Yeah, you could, if I kept the confidence interval the same length, then I could say, well, what would I have to do with the alpha to make that the same length? And I could ask, that's a little bit more complicated question. I bet on a homework, you could figure that out. On a quiz, you'd have to kind of think, and I probably wouldn't ask something that involves that mix of things on a quiz. Yeah.
So if you could have the standard deviation, that would be a good example.
Yeah, right. So if you get a better individual estimate, that's a, you know, by a factor of 2, that's as good as sampling 4 times as many people. Right. So that might be a good use of your time. For instance, pollsters, think about this, right? How can I get a good sample of people, right? How do I know that each person is a representative sample? There are now pollsters for elections that try and sample based on the internet, right? They pop up these polls, and maybe some of you have seen these in browsing. And there's been questions of how accurate are these? They can collect a lot, they can increase n a lot, but probably sigma is also increasing because it's really a good cross-section of people. They used to be able to get good estimates by calling landlines at random. How many of you could pick up a landline at some point, like in your day? Okay, maybe, yeah. I have one in my office that's almost entirely the wrong number at work, but I don't have one at home, right? So that's no longer a good thing. Cell phones, when you pick up, when you actually answer a poll on a cell phone, you know, right? So how do you get sigma to be a better, you know, sigma is how reliable is your individual estimate, and it's how many estimators you get, and you got to balance those. Yeah. So, okay, great. So if this makes sense, you'll do well in the quiz, and we're going to do one more lecture on confidence intervals. We're going to see what happens if you don't know sigma. Right? If you don't know sigma, then what should you do? Turns out that's not too hard, but a little tweak on what we've already done. Okay, great. Good luck on the quiz. And if you haven't picked up a printout for homework 6, I've got one available up here.
I have a quick question.
Oh, sure. Yeah.
And then I put it in chat, and I got some reply to you.
Oh, okay.
I just wanted, it's more of a homework question.
Oh, okay. Yep. Oh, yeah. I see. This is the direct message to me. Yeah. Okay. Yeah. Yep. Yeah. Let me look at that now. Yeah. So, yeah. So what you should do is send me.
The teacher or professor already sent you that.
If you send me an email, I will make sure this is probably taken care of. It'll be.
Do you want me to?
Is probably taken care of. It'll be.
Do you want me to just?
Would lose 20%. But up to 3 days from, say, for homework 5, 3 days from midnight, you would not lose anything.
So 3 days. So that would be Saturday at midnight, and then Monday is the last day I could turn it in.
Yep,
so
that's right.
And then, do you want me to just resend you the letter that the CDA sent?
No, the letter I've got that in files. Just make sure you send me an email. It will make sure that I